Hi everyone, in this video, we're gonna explain about what is Green's theorem, a little background about Green's theorem, and also some example where we apply this theorem. Now, let's look at the mathematical definition and core requirement of Green's theorems. To apply this theorem, we must define specific geometric boundaries. First of all, is C. C is represent a closed, simple curve with positive orientation, meaning it runs counterclockwise. The second point is R. R is the 2D plane region completely enclosed by C. And the last point is, for our vector field component, P and Q, they must possess continuous first order partial derivative across the entire region, where this theorem allow us to express this relationship in two distinct mathematical forms. The first form is the standard form. This converts a line integral along the boundary curve into a double integral over the enclosed region. The second form is the vector form. This form relates the tangent line integral of the vector field to the double integral of its curl. Physically, it proves that the total microscopic circulation along the boundaries is equal to the sum of all microscopic rational force inside region R. Next, we will jump to the applicable conditions. To apply Green's theorem, the following condition must be met. The first condition is closed and simple curve C. The curve must be form a complete loop, start and the end point match and cannot intersect itself. The second point is positive orientation. The line integral along boundary C must run counterclockwise, which is it keeping region R to the left. And the last point is differentiability. Function P and Q must have continuous first order partial derivative across region R. Now, let's move to the non-applicable conditions. There are three conditions where Green's theorem fails or cannot be used. The first condition is open path. If the curve does not form a loop, standard line integral or the fundamental theorem of line integral must be used. The second condition is discontinuities. If there is a point inside the region R where the function P, Q or their partial derivative are undefined, the theorem will be failed. And the last condition is self-intersection curve. The simple curve restriction is broken by figure 8 curve or pathway that cross themselves.
Next, let us look at the historical background of this principle. Green's theorem is named after George Green, a British mathematician who lived from 1793 to 1841. To emphasize, Green was largely self-taught and worked primarily as a grain miller. In 1828, he self-published an innovative paper titled An Essay on the Application of Mathematical Analysis in the Theories of Electricity and Magnetism. In this work, he introduced the concept of the potential function, which became a cornerstone of modern physics. Interestingly, Green's original essay did not explicitly state the 2D boundary formula we use today. Instead, a geometric version was actually published later by Augustin Louis Cauchy in 1846. Furthermore, Green's work remained entirely unknown until 1845, which is 4 years after his death, when the physicist Lord Kelvin discovered a copy and introduced it to the European scientific community. Now, how is Green's theorem applied in the real world? While it appears theoretical, it is a highly practical tool across various engineering and scientific fields. First, in physics and mechanical engineering, the theorem simplifies path-dependent force circulations. It allows engineers to convert complex line integrals, such as work done along a closed path, into simpler double integrals over an enclosed surface area. Second, in fluid dynamics and meteorology, it is used to measure fluid circulation and net flow. This is essential for modeling weather systems, ocean currents, and aerodynamics. Third, in electromagnetism, it helps physicists map out two-dimensional magnetic fields and electric potentials to optimize electronic systems. Finally, a famous mechanical application is found in geography through a device called the planimeter. The planimeter calculates the area of irregular shapes on a map simply by tracing their boundaries. The device physically computes the line integral around the perimeter, which, thanks to Green's theorem, that accurately yields the enclosed area. This shows how a vector calculus identity directly solves practical engineering problems.
Now, let's go to the first question, which asks us to evaluate a line integral using Green's theorem. As shown in figure 1, our curve C forms the boundary of a semicircle on the left half of the plane, bounded by x squared plus y squared equals 25. Now, notice that the orientation is counterclockwise, starting from point 0,5, tracking along the circular arc down to the point 0, -5, and returning straight up to the y-axis back to the start. Alright, so let's walk through how we solve this step by step. To apply Green's theorem, we first identify our functions p and q from the line integral. Here, p is equals to yx squared and q is equals to -x squared. Green's theorem allows us to convert this line integral into a double integral over the enclosed region D by using the formula. Taking the partial derivatives gives us an integrand of -2x minus x squared. Since the region is a half circle, switching to polar coordinates makes things much simpler. Our radius r ranged from 0 to 5, and because it is the left hemisphere, our angle spans from 1/2 pi to 3/2 pi. By substituting x equals to r cos theta and adding the Jacobian r, we get our fully set up polar integral. Now, for evaluation, we are going to first distribute the r and integrate with respect to the radius r, evaluating it from 0 to 5. This simplifies our expression nicely, leaving us with a single integral in terms of theta. So, we are going to rewrite cos squared theta using a double angle identity to make it easy to integrate. After computing the definite integral from 1/2 pi to 3/2 pi, we arrive at our exact analytical solution, which is 500/3 minus 625/8 pi. Putting that into a calculator gives us approximately -78.7703. So, to ensure our manual calculus was completely flawless, we are going to cross-verify our setup using Maple software. By defining our vector fields M and N, computing the standard 2D curl expression, and running the polar integration command, Maple outputted the exact same symbolic value of 500/3 minus 625/8 pi. Converting this to a floating point decimal yields -78.7702594, which perfectly confirms our manual results. Finally, let's talk about what this number actually means physically. The fact that we got a negative result tells us that the vector field exerts a net clockwise circulation across this region. Because our path of motion along the boundary was counterclockwise, the field's forces were generally pushing against us, opposing our movement. In physics terms, this means that the vector field performed negative work on an object travelling along the curve C.
Then, we will move to the next question. Calculate the line integral x squared y dx plus y minus 3 dy with the limit of C, where C is a rectangle with vertices of 1, 1, 4, 1, 4, 5, and 5, 1. As we can see on figure 2, it illustrates a rectangle with the mentioned vertices. Next, for manual calculation, first we will determine the p and q from the integral. So p will be equals to x squared y and q will be equals to y minus 3. And then, by applying the Green's theorem, we will get the integrate of p dx plus q dy. It will be equals to double integration of del q over del x minus del p over del y, where dA. Next, we will substitute p and q into the formula. So, we will get double integrate of y minus 3 del over del x minus x squared y del over del y, dA. Next, we will find the differentiation of p and q with respect to y and x respectively. So, when we differentiate q with respect to x, we will get 0. And then, when we differentiate p with respect to y, we will get x squared. Since x goes from point 1 to 4 and y goes from point 1 to 5, we can set the limit of x and y into the theorem and evaluate the theorem as below. So first we will integrate with respect to y, and then substitute the limit of from 1 to 5, and then we will get the next equation where it will be the integration of -4x squared from 1 to 4, and then we will integrate with respect to x. So we will get -4x cubed over 3 with the limit from 1 to 4. And then after we substitute the value of 4 and 1, we will get the final answer, which will be equals to -84. This is the Maple command that we use, and then this is the output that we receive from the command. By converting the boundary line integral into the double integral over the region R, the manual integration yielded a precise result of -84, which was successfully verified through Maple software. The negative outcome provides important physical insight, proving that the vector field exhibits a net clockwise circulation that directly opposes the standard counterclockwise movement along the path.
In conclusion, this project successfully demonstrates the power and efficiency of Green's theorem in simplifying complex line integrals by converting them into double integrals over enclosed planar regions by analyzing two distinct geometries, a semicircular region in question 1 and a rectangular boundary in question 2 shows that the manual step-by-step calculations are perfectly aligned with the computational outputs generated by Maple commands. The negative result obtained in both problems indicate that the respective vector fields exert a net clockwise circulation, meaning the field force generally oppose counterclockwise movement along the path. Ultimately, this project highlights how bridging theoretical vector calculus with modern mathematical software provides a deeper, highly verifiable understanding of force, field, and circulation in two-dimensional space.